All right. Hello, everyone, and welcome back to Calculus. So in our last video, we talked about first derivatives and how they were related to the shapes of the graph. In particular, in regions where the first derivative is always positive, then you know your original function is increasing. And in regions where f prime is negative, you know that f is decreasing. So what we're trying to do today is we're trying to kind of figure out a similar thing for what the second derivative tells us about the graph of f. So let's go ahead and just build an example. So I'm looking at the graph of f of x and f double prime of x here. And I'd love if you would pause here for a minute and think about what intervals this graph is positive and negative on, and then kind of go back to f of x and look at those same intervals and see if you can say anything about the shape of f of x. When f double prime is positive or when f double prime is negative, what does that seem to be correlating to in the graph of f of x? So go ahead and pause here for a second and try to think about those things, and then I'll pull you back in with the answer. Okay, so should be back with having thought about that. So I'm going to think about regions where f double prime is positive. So that means I look at the graph of f double prime of x, and I should be looking at where that is above the x-axis. So see, that is in that region, but I'm just going to think about the intervals where that's true. So in these intervals, my graph of f double prime is positive. And then in these intervals, my graph of f double prime is negative. So I'm going to go translate these over now to the graph of f of x and see what seems to be going on. So let's see, I had f double prime was like positive in that region, and again in this region, and here, and here, and here. And then let's see, f double prime was negative in this interval, this interval, this interval, this interval, so forth. Okay, so it seems like the pattern is that when if f double prime of x is positive, then it seems like f of x has a shape where it's kind of up, like kind of opens upwards. And it seems like whenever we're seeing that f double prime of x is negative, then those seem to be the places where f of x looks more like it's opening downwards. So I'm gonna kind of formalize that on the next page, but that's more or less what we're seeing. So in these regions where we had negative f double primes, in those regions where we had negative f double primes, those seem to be the regions where f is kind of facing down. And in the regions where we had positive f double primes, those seem to be the regions where f is facing upwards or opening upwards. Okay, so that is sort of our intuition. And it turns out that that is just generally true. So that, like, we kind of took that from this one example, but if you played with a bunch of different graphs, this really is sort of the idea that we should get. And so if I state that a lot more carefully, this is what we've just figured out. So let's take a continuous function f of x that's continuous over a closed interval. And let's make sure it's also twice differentiable over the open interval AB. In other words, what this means is that f double prime of x is defined. That's what twice differentiable means, right? Because just differentiable means f prime of x is defined. Now we're looking at twice differentiable, so f double prime of x is defined. Okay, so if f double prime of x is positive for all x's between a and b, then f of x is concave up, and that is truly just means that the shape is upwards. I think concave up like a cup. So whenever f double prime is positive, then our original graph is concave up like a cup. And if f double prime is negative, then our original graph is concave down. So our original graph, f of x, should be concave down like a frown. So concave up are the regions where you can hold water on the graph. Concave down is where you can't hold water in a graph. Okay, so let's go ahead and see an example of sort of doing this fully out. So we're told that our function is x cubed plus 7x plus 2. And we're asked to find all regions where we can guarantee f of x is concave up or f of x is concave down. So that means we're going to need to calculate f double prime and figure out where f double prime is positive or negative. So let's see, f prime of x is going to be 3x squared plus 7. And so that means f double prime of x is going to be 6x. Okay, so let's go ahead and do a number line if I want to figure out everywhere that it's positive or negative. I'm going to do a number line. So down here, I'm going to label my x values. And above the number line, I'm going to label sort of sign of f prime, f double prime, or sort of other information. So in particular, first thing that I need to do is I need to label the zeros of f double prime. So f double prime of x equals 0 when x is 0. So when x is 0, I know the sign of f double prime is that it's going to be 0, so it's not positive or negative. And then I'm going to do some test points. So I'm going to test maybe x equals -1. So f double prime of -1 is 6 times -1, so -6. So I get to conclude that in this whole region, f double prime is going to be negative. And then similarly, if I test x equals +1, then f double prime of +1 is going to be 6 times 1, so it's 6. So f double prime is going to be positive in that region. So all this number line is telling me is that up to x equals 0, f double prime is negative. At x equals 0, f double prime is 0. And then above x equals 0, f double prime is positive. So now what we need to do is go back and sort of interpret this in terms of our original question, which is asking us about when f is concave up or concave down. So this number line tells me that f is going to be concave down on the interval where f double prime is negative. So concave down on -infinity up to 0, not including 0, because f double prime isn't negative at 0. And f is going to be concave up whenever f double prime is positive. So f is concave up on the interval from 0 to infinity, again, not including 0, because f double prime is not positive at x equals 0. All right, so that's going to be sort of our general process for figuring out concavity of f on different regions. So you go through, you figure out f double prime of x, then you create a number line, you find all the zeros of f double prime, then you do your test points in between, and then you go through and you interpret that in terms of your concavity. Okay, so let's do one more example before I let y'all do one on your own. So I'm given that f of x is cosine of 2x, and I want to find all intervals where f is concave up and all intervals where f is concave down. So again, first thing, I'm going to find f double prime of x. So let's see, this is a chain rule thing. So I need to do the derivative of cosine of 2x using chain rule. So I'm going to have the derivative of cosine plug in my inside function times the derivative of my inside function. So I get -2 sine of 2x. And then for f double prime of x, I'm going to take the derivative of that, and I'm going to again have a chain rule going on. So my -2, my constant comes with me, and then of the derivative of sine, which is cosine, plug in my inside function, and then multiply by the derivative of my inside function. So by chain rule, in total, I should be getting -4 cosine of 2x. Okay, so then I need to go ahead and do my number line. It's going to be actually like infinitely many intervals where f is going to be concave up and concave down. So I'm just going to do kind of enough of the number line for us to really kind of get the pattern. But let's see. So I want to first label places where cosine of 2x equals 0. So cosine equals 0 when my x values equal 0. So at pi over 2 and 3 pi over 2. So those are the angles that I would need to plug in. So 2x equals pi over 2 would mean that I'm really just looking at x being pi over 4. So at pi over 4, f double prime would be 0. And then at 3 pi over 4 as well, we're going to have f double prime be 0, because then that would mean plugging in 2 times 3 pi over 4. So that would mean plugging in 3 pi over 2 to cosine, which would get us to 0. And then let's see, so the next place where cosine equals 0. So again, I'm just kind of thinking through the unit circle here. So I've looked at cosine equals 0 at this point, cosine equals 0 at this point. Then I'm going to wrap back around. So I thought about that as pi over 2 at first, and now I'm going to think about that as pi over 2 plus 2 pi. So I'm going to think about this as, let's see, 4 pi and 5 pi over 2. So when I plug in 5 pi over 2 to cosine, I would get 0. So this equaling 5 pi over 2 would really mean that I'm looking at x value being 5 pi over 4. And so forth. So you can kind of see that the pattern seems to be, and as you and you can double check and be sure, the pattern is that we are just adding. Sorry, did I just erase? Yes, pi over 4. Okay. So the pattern is that we're just adding multiples of pi over 2. And that seems to be what's getting us all of our zeros. And so any sort of added or subtracted copy of pi over 2 will get you all of your zeros. So these are all the x values where f double prime equals 0. And then let's go ahead and do our test points in between. So for example, let's see, a test point of x equals 0 would have me looking at f double prime equals -4 times cosine of 2 times 0, so cosine of 0. So that's going to be -4 times 1. And so in this region, f double prime is going to be negative. If I test, let's see, x equals pi over 2. Then f double prime equals -4 times cosine of pi. Cosine of pi is -1, so I get -4 times -1. So I get positive in this region. And so forth. You keep testing your points, and you'll see that you keep sort of going back and forth between negative and positive. Okay, so this is just part of the number line, but like we should now be able to see the patterns of what's going to be going on and when f double prime will be positive and when f double prime will be negative. And it's just this alternating pattern. Okay, so with that, we can go ahead and do our interpretation. So f is going to be concave down whenever f double prime is negative. So f is going to be concave down in these regions, and sort of pattern going out across my full number line. So I'm going to just kind of give enough of the pattern that you're going to be able to see it. So I'm going to have intervals. That's why I'm dotting. So I'm saying the intervals that would happen before this. Union, the interval at negative pi over 4 to pi over 4. That's an interval where f double prime is negative. Going to add on the interval from 3 pi over 4 to 5 pi over 4. Going to add on the interval. Let's give one more so it's clear that we're just adding sort of pi over 2 between the endpoints. So the next interval that would work would be 7 pi over 4 up to 9 pi over 4. And then union, and then this dot again. Running into the stuff. So dot meaning continue this pattern on. So that is one thing that we get to conclude from our number line is in all of these regions, f is going to be concave down. And then similarly, we can talk about where f is concave up. And it's going to be on all the regions where f double prime was positive. So we're going to do our dots because, again, we're going to have infinitely many options. And then I'll just label a few of them to kind of be able to give my reader the pattern. So I would have negative 3 pi over 4 up to 4, or pi over 4, negative pi over 4, goodness. Union pi over 4 up to 3 pi over 4. Union 5 pi over 4 up to 7 pi over 4. And so forth, continuing that pattern sort of in each direction on my number line. And so we found all places where f is going to be concave up and concave down by looking up a sign of f double prime. And using a lot of our unit circle memory. Okay, so with that, I'm going to give y'all a moment to go ahead and try a problem yourself. Note that in this problem, I've actually already given you f double prime of x. So you don't need to take any derivatives or anything. You can go ahead and just start thinking about the sign of f double prime of x and where it's equal to 0. But I'm giving you that f double prime of x equals natural log of x divided by negative x. And I want you to go through and try to figure out all intervals over which you can guarantee that f of x is going to be concave up or concave down. All right, so go ahead and pause here and try to do that. All right, hopefully you did actually pause and try this yourself. So what you should have found is that f is going to be concave up between 0 and 1 and concave down between 1 and infinity. Because f double prime is positive from 0 to 1 and f double prime is negative from 1 to infinity. Notice that we don't have anything before x equals 0, and that's because our function will not actually be defined there. So at x equals 0, we've got an issue with our denominator, and then natural log of x is not defined for negative values, so our function just does not, or f double prime, we don't have any information about the sign before x equals 0. All right, so that is how the second derivative is related to the shape of the original function.